Greetings to you guys. I hope you are all doing very well at this moment of time. Today I'm going to take you to work energy and power. A very easy topic. If you're going to make sure that you listen or you watch this video, you watch all of it. Okay guys, please do not forget to like, share and comment and hit the notification bell so that you can be notified when we upload new lessons. And the most important thing, do not forget to subscribe. So work energy and power is a paper one topic. So it's 3 in 1. We're going to talk about work, we're going to talk about energy, we're going to talk about power. But now we're going to start doing work. We all know what work is, but you must define it in terms of physical science or in terms of physics or the exam guideline. But let me just explain this work term or work word. The word or the term work is actually, when I do something, I work. I don't know if you understand that. When I do something, let me say, for me to clean the house, I am working, right? Then when I clean the house, let me say now it's dirty. Clean the house because it is dirty, right? So if it is the house is dirty, I have to clean it. I have to make it clean. So we will say that you have done work. Why? Because from the state of its dirtiness to the state of its cleanness, there's something that was done. That is work, or that what we call work. I don't know if you understand that. So work is everything that we do in our daily living or in our daily lives. But now physical scientists or physics explains it in more details, which is what we're going to do today. All right. Actually, when you work, it's actually the movement or the displacing of an object or of whatever from one state to another state or from one point to another point. I don't know if you understand that. As I made this example, that when you find your house, actually you don't have a house, when you find your parents' house dirty, what is it that you will do if you are not lazy? You will clean it. Then all the papers and everything that makes the house to be dirty, you will take everything and throw them in the rubbish bin or in the trash bin. Then after that, you make sure that you do what you clean the house or you clean that specific area. Now, what is it that will make us to say that you have cleaned the house? It is when we see that the dirtiness of the house is no more. Now the house is clean. It means that you did what you've done work. So work is actually moving something. It's actually the displacing of an object. I don't know if you understand it, but you must also look it in your exam guideline. Define it the way the exam guidelines states or says that you must define it. Okay, work has its own formula, which is W equals F delta X cos of theta. So this formula represents what we call work, where W is the work done by a force. Work done by a force, meaning that for me, that's why I'm saying that for me to say I've done work, I must move whatever object from the point or the point that it was placed on, then you move it to another point. So you have done work. Why? Because you apply force. There's something or there's this energy that you applied on that object. I don't know if you understand that. That is why when you mop the floor, what you do is that you don't just take a mop and put it maybe on top of a tile, but there's energy, there's a force that you must apply on the mop so that it can wipe or so that it can clean the floor. I don't know if you understand that. So that's why we're saying that work is done by what? By a force, or W, work done by a force measured in joules. Then F is the magnitude or the size of the force doing work measured in Newton, right? Now delta x is the magnitude of the displacement measured in meters. So for an argument's sake, let me say, you are given millimeters, you multiply by 10 to the power negative 3, so it can be in meters. If you are given centimeters, you multiply by 10 to the power negative 2, so that you get meters. I've never seen this, but let me say you come across this thing, you can use it, or you can convert. Therefore, theta is the magnitude of the angle between the force and the displacement, or between the displacement and the force. So this is the formula of what we calling work. This is the formula of what we calling work. So we know from Newton's second law, or from Mr. Isaac Newton, that for an object to move, there must be forces that are acting on that object, that are causing the object to move. Mr. Isaac taught us about applied force. I don't know if this is the correct spelling, but as we know, there's no one who's going to mark me. Frictional force, measured in Newton. Weight, not the one that says someone must actually wait or stop. Weight, or gravitational force, or gravity, a very special force, and normal force. We're going to talk more, or we're going to talk a lot about these forces that you see on your screen there. Meaning that for an object to move, that object, or there must be forces that are doing what? Are doing work on that object. When we explain in terms of Newton's laws, for this block A, for it to move, there must be a force that is applied on the box or on the block for it to do what? To move. Same thing applies when we come to work. Since we say that W is the work done by a force, meaning that for a work, or for work to exist, or for work to be done, there must be a force that will be applied, or that will be present in whatever object you are referring to. I hope you guys understand that. Okay, Mr. Isaac taught us that we have F and we have F net. F is the single force on an object doing work, and F net, it is the sum of the forces on an object that are doing work. But in terms of Newton's laws, do not actually confuse yourself, since I'm saying that F is the only force. Okay, let me say this in this way, or let me say it in this way. Yes, force is a single, or F is the single force acting on an object, but F net is when we are summing forces that are acting on an object. So this is W, a single force, or here we'll be having a single force doing work. This is work done by a force, but work net, or W net, is when we are having, or we are summing the total sum of work done by FA, work done by FF, work done by FN, and work done by FG. We call them work. After we do what? We add those works. I don't know if it's works or what. But what I'm saying is that when we add maybe FA plus WFF plus WFG plus WFN, so the answer that we're going to get here is what? It's work net or W net, total work on network. Okay, we have work done by applied force, work done by frictional force, work done by Fn, work done by Fg. Alright, work done by Fa, it will be Fa delta x cos of theta, meaning that the work that is done here is done by the applied force. Work done by frictional force, and we have work done by normal force, and the work done by gravity or gravitational force. But we know that mg is, Fg, mg, delta x cos of theta. This is what we know, this is what we have. But we're going to talk, we're going to explain this. Make sure that you focus here. Fn, or work done by normal force, is always 0. Why? Because when we define normal force, we're saying that the force exerted by surface on an object with which it is in contact and which is perpendicular to the surface. Meaning that when we put the perpendicularity of the definition, this is 90 degrees, right? Meaning that when we write cos where there's theta, we substitute 90, it will give us 0. So all the time, work done by normal force is 0. Why? Because it is perpendicular to the surface, and the word perpendicular tells us about the 90-degree angle. I don't know if you understand that. Then WFG is 0. Why am I saying it's 0? It is 0 on the horizontal surface. Do you understand that? Work done by gravity is 0 on the horizontal surface. Only on the horizontal surface, not all the time as normal force. Look at this. Let me say this is our diagram. Let me draw a force diagram. Here it will be 90 degrees, right? Even here it will be 90 degrees. So normal force and the work done by gravitational force on the horizontal surface, the work done by gravitational force is always 0. Why? Because where there's theta, we'll put what? We'll put that 90 degrees. And it's not always 0 on the work, on the Fg part, on the work done by force, on the work done by gravity or force of gravity or gravitational force. I don't know if you guys understand that, but make sure that you understand it. It's very, very important that you understand this. Okay, let me say we have F1 plus F2 plus F3 plus F4. It becomes F net, right? Why? Because we summed the forces. Even here, when we sum FA, work done by FA, work done by FF, work done by FN, work done by FG, we're going to have something that has the net part or the net term. We won't say F net, but we'll say W net, which is work net. When we sum all of the work done by the different forces. I don't know if you guys understand that, but this is very important for you to know. In a statement, you'll be given delta, you'll be given that force if it's FA, you'll be given that force if it's FF, you'll be given that force if it's Fn, but we know that Fn is 0, right? You'll be given the mass, and you know that the gravitational constant is 9.8. You'll be given delta, they will tell you the delta or the displacement between, the displacement of whatever scenario, whatever case. But now, they won't give you the angle of theta. And many people are struggling on finding angle theta. So this video is going to make sure that you understand how you're going to find the angle theta. And after finding it, or after knowing how to find it, make sure that you forward it to your relatives, forward it to your neighbor, forward the video to your classmates, so they can get this help, so they can understand how to find or how to get the angle theta. Right? So make sure, guys, that you understand this. Make sure. All right. Let's show you. This is the formula, right? From its starting point, or this is the formula of work when there's no force acting on it. This is actually the definition of work, but you must define it in terms of what? In terms of the exam guideline. So, when you do something on an object, that's an action done on an object. When you move it, you are actually displaying or displacing, displacing the object from one position to another position. So the displacement or the action that displaces the object, that's work, right? But you must define it in terms of the exam guideline. Okay, we want to show you how to find the angle theta, or the magnitude of the angle between the displacement and the force. So let's focus on the work done by applied force. Then we'll just talk about those other ones. And you must understand Newton's second law, the free body diagram, as well as their definitions. Applied force. So let me draw something like this. The x-axis. This is 0, this is 180 from a Cartesian plane, right? So it's either my object is going up or is going down to the right or to the left. The position that I tell my learners to take right. The motion of an object is always going to the right, meaning that it approaches this 0, it is going to that 0. Make sure that you listen to this. Let me say I have an object. Then the motion, or we apply a force. Then the motion of an object is to the right. Do you understand that? This is Newton's laws. Do you understand that? The motion of an object is to the right. And always the position of the motion is to the right, or the direction of motion is the direction of motion instead of the position. The direction of motion, we take it all the time to be or to face the right position, or the right axis, which is 0. I don't know if you understand that. Whether the object is going up or whether the object is going down, is going to the left or is going to the right, always make the direction of motion to be to the right. I don't know if you understand that. Let me just do this example so that you can know how to write the angle theta there. After that, we do another example so you can understand this. Now, FA and the motion, they are going to, or they are going the same direction, meaning that they are going to the right. Even if they were going to the left, as long as they were going to the same direction, we're going to make them to go to the right. Okay, let me just do this. So this is our object, right? This is our object. Now the motion of an object is going to the right, right? Then what again? Even the force applied is going to the right. Meaning that where FA is pointing at, that number or that angle, that's the angle of theta. Meaning that the angle of theta here is 0. So it will be FA delta x cos of 0. And on the statement, on the question, will be given all of these two variables. You won't be given this theta. I don't know if you understand that. Okay, let me say the object was going up. This is block A, the object was going up. This is what? The motion. This is the motion and the force applied. You can see that both the forces, both the applied force or the force in the motion, they are going in the same direction, but we know that, or we just use a free body diagram. This is 0, this is 180. We don't care if the object is going down or is going up or to the left or to the right. We always use this one. So this is 0. Now this is the object, the motion of an object is to the right as well as the FA, right? They are pointing in the same direction. Let me say they were going down, both of them. The motion and the applied force. We're going to make them, or we're going to take the direction which is right. So where FA is pointing, that's the value of the theta, which is 0. I don't know if you understand that. That's very important, guys. That's very important. Okay, let me explain this. You have an object that is going to the left, or the motion of an object is to the left. Since the motion of an object is to the left, you are given delta x, for example, is 3 meters. You are given the value of FA, let me say it's 20 Newton. Then they want you to calculate the work done by applied force. This is what you do. As you can see that both the motion and the FA, they are going the same direction. You do this. You draw your free body diagram, or it can be the force diagram. So this is FA and the motion. Remember they're going the same direction, so you always assume, or you always change it as if they were going to the right. Then this is 0, then this is 180. Then where FA is pointing at, is pointing at 0. So that 0 is the angle that you put there. I don't know if you understand that. Even if it's on an inclined plane, you do the same thing. 0, 180. This is a Cartesian plane, or it's a free body diagram. Then now this is the object, right? This is FA, F applied. Okay, let me say it was going up and inclined, and the motion is up. Now they are both going in the same direction, meaning even here in this diagram, in this free body diagram, they must go in the same direction, or towards the same direction. Where FA is pointing at, that angle there is theta, meaning theta is 0 on that scenario. I don't know if you understand that. It's not always that you will find FA being 0. It's not all the time that FNet is always 0. No. But in most cases, it happens. But let me show you this one. If an object, or if FA is not pulled, theta is 0. Sometimes it can be 180, but we'll come to that scenario or that story. Let me say FA is pulled at an angle maybe of 80. Of an angle of 10 degrees. Let me say it is pulled. Okay, let me make it slightly bigger. Okay. That cloth is actually wet. Okay, this is FA, then it is pulled at an angle of 10. Sorry about this, guys. The cloth is wet. Let me try to use another one to remove. Oh my goodness. Okay. This is FA, and the angle here is 10 at least. This is object A. Now the object is going to the right. Do you see this? Now you draw that free body diagram. You know that it's 180, and here it's 0. So these ones, they are not going to the right. Okay, the motion is to the right? But FA is not to the right, but it is pulled. So when it is pulled, this is what you do. You take that angle that FA is pulled at, becomes the angle of theta. But if they were going in the same direction like this, you're going to take the 0. If they were going in the same direction. I don't know if you guys understand this. It's very, very important. Even if the FA was pulled like this, we're going to take that angle that is placed there. But now, if you are given something like this, you do what I've done on the previous point or the previous part. So here it will be work done by applied force equals FA delta X cos of 10. Only if it is pulled. Not when it is on an incline, because you can be given an angle here. So it's not like you're going to take this angle and substitute it where there's theta. No, you don't do that. You only do it when FA is pulled. I don't know if you understand that. That's very, very important. Okay, we come to frictional force, or work done by frictional force. When we define frictional force, we're saying that the force that opposes the motion of an object. Opposes what? The motion of an object. Let me say we have object A, this is FA, then the direction of motion is to the right. You draw that. Remember, the motion is always going to the right. This is 180 and this is 0. This is our object. This is FA, but we are not looking for the work done by FA. We know that work done by FA in the motion, work done by FA in the direction of motion is to the right. We are heading to 0, but it's not always 0. It can be 180 and it can be the angle where FA is pulled on or pulled at. Okay, so work done by frictional force, FF delta X cos of what? It's not 0, because FA opposes the motion. Since FA is going towards 0, FF will go towards 180. So it becomes 180. I don't know if you guys are understanding this. Then let me say we have something like this again. We are going to the left. The object is going to the left. When the object is going to the left, it's not like theta will be 0. No, it's not like that. But remember, you take motion all the time as if it's going to the right. Now this is FA, this is 0. Now frictional force opposes what? The motion. So frictional force becomes 180 again. I don't know if you understand this. Even if the object is going up, we say the object is going up, this is the motion, right? This is FA. This is FA and the motion. Since both of them, they are going the same direction, you take them as if they were going to the right. So this is 0 degrees, this is our object, and this is 180. Force, okay, the motion is to the right, and applied force is pointing at 0. But what about the frictional force? Because now we're calculating the work done by the frictional force. So it will oppose the motion. So it becomes 180 again. I don't know if you understand me. This is very, very important, guys. We don't care if the object is going down or the object is going up, but we take the motion, making it to point to the right or to be in the right direction or easterly direction. I don't know if you guys understand this. Even when the object is pulled, we don't care. Even when the object is pulled, this angle will be the angle of theta. But when it comes to frictional force, when it goes to the right and we take 180 as the angle of theta, even when it's like this, the object is going up and inclined in the direction of motion is up. This is FA. Both of FA and what and the motion, they are going towards the same direction. So it will like this. This is motion, right? This is 0, this is 180. Now this is the applied force on this scenario here. This is applied force, and the frictional force opposes the motion, right? So it will go to 180, which will be force WFF equals FF delta X cos of 108. So in most cases, the theta, when we want to calculate the angle, I mean the work done by force apply, work done by frictional force theta, most of the time it is always 180, but there is a time where it will be 0. I don't know if you understand that. It will be 0. Let me just explain that one, then we go to work done by gravity. Let me say this is U. Now this block is on a slippery surface. It is moving on its own. Let me draw you here. It is moving on its own. So you want to stop it from moving. So as you want to stop it from moving, okay, these are your hands. You apply a force actually. You want to actually pull it towards yourself, meaning that the force that you are actually applying on the object, since it is moving on its own, is the applied force. Now the direction of motion of the object is towards, okay, let me erase this whole thing so that you can see what I'm trying to explain here. But what I'm saying here is that work done by FF, its angle, it won't always be 180. Let's go back to what I wanted to explain here, or what I want to explain, so that we can talk about work done by gravity. Then after that, we do some other things. Okay. This is the object, and this is you. The object is on a slippery surface. It's on a slippery surface. Now this object is moving on its own without a force being applied on it. That happens. So as it is moving, so the direction of motion before you apply a force on it, since it is moving on its own, this is you. This is you, and you are not actually smiling there because the block seems to be heavy. So this is you. I want to explain this part, that theta on the work done by frictional force, it won't always be 180, but it can be something else. Let's find out something else. Now, the blocks of the box is moving on. It is moving on its own, right? Now, since it's moving, it was moving to the left direction, and you apply a force, you are pulling it towards yourself, meaning that this is applied force that you are pulling, meaning that the motion of an object now and the applied force, they are not going in the same direction. I don't know if you understand this. Do you guys, I don't know if you guys understand this. This block is moving without a force being applied on it, since it is in a slippery surface. Now you want to stop the box or the block. Now when you apply a force, you're actually pulling it towards yourself. Now you can see that the motion of an object is going to the left, but the force that you're applying on the object is going to the right, meaning that these two things, the force applied and the motion, they are not going in the same direction. So it will make, because we know that the motion is always going to the right? But the force applied is not go. I don't know if you guys are going to understand this. Motion is always going to the right, but FA, it won't go in the same direction with the force applied. I don't know if you understand that. That will make the force applied to become 180, as well as the frictional force to become 108, since it will be opposing the direction of motion. I I don't know if you guys understand this. This is very, very important. Make sure that if you didn't understand this, make sure that you pause the video and listen to it again. So the work done by frictional force on this scenario, it will be FF delta X cos of 180. Even the work done by FA, if you understood this, if you didn't understand it, make sure that you actually pause the video and listen to it again, because this is very, 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 very important. This is very important. So how will FF change? Let me say the block was going to the right. The motion of an object, before you try to stop it, was going to the right, and you apply a force. When you apply a force on it, you want to do what? You want to pull this object towards you. I don't know if you understand that. You want to pull it towards yourself. And now this becomes the FA magnitude. Now when you draw this thing, this is 0, this is 180, right? Now the motion of an object is always going to the right, but FA is not now going to the right, right? Because they're not going the same direction. So it's not going to point on what? On the F, on the 0 angle, but it will point on that angle there. I don't know if you understand that. That makes both of FA and FF to become 180. So FF can be 180. It's not always like it's going to be 0. I don't know if you guys understand this. It's very, very important. And theta of the work done by the frictional force can also be 0. If you understand this scenario, make like a scenario for yourself where you are going to deal with the frictional force on what I've explained here on the work done by applied force, that it's not always going to be 0, but it can be 180. So now we'll talk about the work done by gravity. Work done by gravity, or work done by the gravitational force. Why? Because the work done by normal force is always 0. Even the work done by gravity, there are scenarios or there are cases where it will be 0, but only if it's in a horizontal surface. Work done by Fg, it will be mg delta x cos of theta. After simplifying it, so this board is actually, I'm using a wet cloth here, so it will be cos of theta. Let me say this is our object. The direction of motion is to the right, and the force applied is to the right. But we know that when we talk about force of gravity, something like this, it's balanced with Fg. With Fn, or the normal force. So we are not using this now. Well, because the direction of motion, okay. Actually, I made a mistake here. Okay, I didn't make a mistake. The direction of motion is to the right, right? When the F applied is to the right, but we're not focusing on the right direction, but it's up and down, as you can see from the from the free body diagram. Now our object will be like this. So for the work done by Fg, it will be mg delta x cos of the 90 here, because it's on a horizontal surface, which is going to make it to be 0. Always it is 0 on what? On the horizontal surface. I'm not saying that the work done by Fg will always be 0 in all of the cases or in all cases, but it will be 0 only in a horizontal surface like this one. Okay. Work done by Fg is Fg delta x cos of theta. So when the object is going up and when the object is going down. When the object is going up, we know that from a Cartesian plane we have 90, we have 270 here, right? When the object is going up, we add 90 plus the angle of theta on the scenario, on the drawing. When it's going down, we take 270 as the angle that's on the downward part, on the downward direction. 270 plus theta. For example, we have something like this. The object is going up an incline. This is the direction of motion. This is FA. Now this is 40. Then they want us to calculate the work done by the gravitational force. So it's FG delta x cos of, you add, since the object is going up, it will be 90 plus this angle, which is 130? I don't know if it's 130. I got this 130 because the object is going up and we are calculating the work done by gravity. You add 90 plus the angle here. And if it was going down, this is FA, this is motion, this is 40. It will be work done by FG, which is FG. We know that FG is mg, right? Delta x cos of, where there's theta, you write 270 plus theta. It will be what? 310. Then you're going to get what? Your answer. I don't know if you guys understand that. Let me say we're given the value of the displacement as 3 meters, and then this is, it has the mass of 3 kg. It will be WFG mg delta x cos of 310, right? We know that mg is 3, 9.8, delta x is also 3 cos 310. Then you punch your calculator. That answer that you get, it will be measured in joules. I don't know if you understand that. This is very, very important, guys. It's very important. Now we're going to talk about positive work, negative work, and zero work. Then the conservative forces. Then we go to energy.